We propose an end-to-end learned optically coded super-resolution SPAD camera that incorporates the joint design of optics and deep network reconstruction for a variety of photon-starving imaging applications. With the advantages of single photon level sensitivity and picosecond level time resolution, SPAD array has emerged to a promising candidate solution for many computational photography tasks. Unfortunately, image sensors with smart SPAD pixels still suffer from the bottlenecks of low spatial resolution and low fill factor. The final data captured by SPAD array is actually the sampling result of a high-resolution image with very low ratio. Therefore, we seek to incorporate both the optimal optics PSF encoding and deep network-based super-resolution method to recover a high-resolution image with a single-shot procedure. The framework of our optical system design is illustrated as follows. With respect to PSF optimization, the PSF kernel for the low fill factor SPAD array is learnt using the end-to-end framework. In each forward pass, the synthetic PSF is convolved with the training dataset. Then the low fill factor sampling model is applied. Later, Poisson noise is added to account for sensorist counting noise after the sampling process. With respect to the phase mask design, given an optimal learned PSF, a high-fidelity phase unit is obtained through applying a Gershberg-Saxton-based phase retrieval algorithm. Eventually, the faceplate is obtained by padding the phase unit and fabricated using lithography and RIA etching. Specifically, the network is composed of three main parts: initial feature extraction, which is composed with two convolutional layers, back projection stages, and a convolutional layer. As the reconstruction step, it introduces an iterative error correcting feedback mechanism to characterize the features in previous layers. The back projection from high-resolution domain to low-resolution domain addresses the mutual dependency. Please refer to the paper for details. Again, the reconstruction is actually implemented by dense, deep back projection networks. Given a low-resolution input from the measurement of SPAD sensor with custom-designed optics, we eventually achieve a 4 times super resolution. We next present some simulated results. We first show a quantitative comparison of several sampling models being tested on 3 standard datasets to verify the effectiveness of the phase mask. The first sampling model is the low fill factor case, same as our sensor model, but without the phase mask. The second model is the full fill factor case. The third and fourth are our model and ground truth, respectively. Clearly, with the assist of our phase mask, the reconstructed results exhibit much closer quality to the ground truth from both visualization and quantitative comparison. Here, we present another example for further comparison. We next present some experimental results. In this implementation, the first figure is directly sampled by our sensor without the phase mask. The second figure is the corresponding reconstructed result. The third one is sampled with our fabricated phase mask, and the last one is its corresponding reconstruction. Again, with the assist of our phase mask, the super resolution result has a huge improvement visually. We have built the prototype for the verification of our framework. It generally includes 2 parts: illumination system and imaging system. For depth and transient imaging illumination, the picosecond laser is scattered by a diffuser and then reconcentrated by a convex lens. For other applications, we simply use a common white light source. As for the imaging system, the light reflected by the scenes is firstly modulated by the phase plate. Then a 50mm lens maps the modulated scene light to the SPAD sensor plane. We next present the results of different applications. First, we show the super resolution results of static scene. Second, we show the super resolution imaging results of a high-speed rotating fan. The third application is super resolution imaging for depth map estimation. Another example of depth imaging. Last but not the least, we show super resolution results of transient imaging. The scene on the right side is reflected by a mirror. another example of transient imaging. In conclusion, we proposed an end-to-end framework to realize super resolution for low spatial resolution and low fill factor SPAD sensor through incorporating optics, sensor model, and deep reconstruction network. Accordingly, we build a single-shot computational super-resolution SPAD camera that can be very promising in a wide range of imaging applications. Thank you for your attention.